Okay, I'm going to give a super brief tutorial on how to model a space station with air resistance so it deorbits. So this program's online. I'll include a link on it, and I also wrote a blog post about it, but I want to go over some of the details because there's some complicated things. So this is in Trinket, but you could use glowscript.org. You could do this running Python on your own computer if you have the visual module installed, but this just works the best for me. I'm going to go through each line, tell you what it does. Okay. This one, scene.user zoom equals false. If I embed a trinket in a blog post and you are scrolling over the page and then you are over the animation and you scroll, it'll like zoom out. So I turn off zooming so it doesn't do that. That's what that is. Okay, line 7 down here. This is just makes a graph and I give it axis labels and so forth. This fast equals false makes Python send the data to Plotly so you get a prettier graph. Now, F1 is the actual graph. So T-graph is temporary graph. That's the holder for the graph. The actual curve is F1. And you can name it whatever you want. Okay, this is the function rho for density. And I give it an altitude and it gives me the density. I got this model from, actually, here's the website right there. And it based the density of the atmosphere as you go up super high on the temperature and the pressure and these different parameters. So I just made a little function here. If the altitude is less than 11,000 meters, you use this. For the pressure, if the altitude is in between 25,000 and actually 11 and 25, use this. And then otherwise use this. Then once you find the pressure, you can calculate the density. So it returns the density. Okay, this parameter right here, A, that's a cross-sectional area of the spacecraft. I just picked some values. You should change these and see what happens. This is the cross-sectional area. I just said, I don't know, I just made up something. Drag coefficient, again, I assume it's not, that's the value, you know, the sphere is like 0.47. It's not a sphere, it's bigger than that. So G, this is the gravitational constant, mass of the Earth, radius of the Earth, starting altitude, I just picked that. Okay. 39, line 39, this is the Earth. It's made as a sphere. It has set the origin, and if you do this part here, texture equals textures.earth, it'll look like the Earth, which is kind of cool. I'm going to make my object orbit in the XY plane, so I want that to be over the equator. So I actually turn the Earth. This line just rotates the Earth, so we're looking at it from the North Pole, but it doesn't really matter. And then here's my misspelled space station. It's Tiangong-1. I put Tiag, but whatever. I stuck with it. It's a sphere also. It's on the y-axis a distance r, radius of the Earth plus the altitude. And then the radius is way too big, but that way you can see it. I made it yellow, and I gave it so it leaves a trail. I gave it a mass. The velocity right here in line 45, this is the square root g me over the total radius. That's the circular motion value. And then I made it a little bit smaller, 0.995 times that, so that it's kind of on its way to deorbit. I give it a velocity vector. I give it a momentum. This stuff right here was, I was adding a second object, but I don't need that right now. Time, the time step. Really, this needs to be a certain size, but I just put 0.1. It probably should be smaller than that, but then it takes too long to run. Calculate the distance between the position and the Earth. I need that for the next line down here. The loop. How long do you run it? I want to run this until it crashes. So I'm going to run it until the position, which is from the center of the Earth to the space station, is less, as long as it's greater than the radius of the Earth. Rate. This tells you how many calculations per second. You can change that. I have to calculate R again every time I get in the loop and it changes. I need to find the location of R. And I need the value of H because that's used in the density function. I need to calculate the velocity from the momentum because I use that in the air resistance. Okay, this is the meat right here. 68. This is the total force. The first part is the gravitational force, and the second part is the air resistance force. And you notice it's negative depending on the direction of the velocity, but it is a vector. Now 70, update the momentum, update the position, update time, and then update the graph. That's it. I'm not going to run it because it's slow. But here's what it looks like when it runs. Let's see if I can pull this over here. Slide this over. So this, it shows you the animation, and then it shows you this is the altitude of the function of time, and then that's where it crashes. So there's lots of things for you to play around with, and you should have some fun.